So in example 4, the author is determining all non-zero ring homomorphisms, both from Z10 to Z20 and from Z20 to Z10. Non-zero ring homomorphisms, remember that the function that maps every ring element to the zero ring, or the zero element, would be a ring homomorphism. Also a group homomorphism. If you're mapping everything to zero, it's trivially a homomorphism. Definitely not one-to-one, definitely not onto. Not very interesting. So we're going to restrict ourselves to non-zero ring homomorphisms. Okay, next sentence. From properties of group homomorphisms, we know that the image of any ring non-zero homomorphism from Z10 to Z20 has these orders. Okay, the author actually didn't say that the best way here. We are focused on a homomorphism from Z10 to Z20. The author didn't really phrase that in the best way. It's implied that we're talking about the image of an element. If A is an element of Z10, the author is talking about the image, the output phi of A, when in the sentence here. We know that the image of any ring non-zero homomorphism from Z10 to Z20. And they're implying, I think the author is implying not only is phi not mapping everything to zero, phi is also not mapping phi of A to zero. So I'm assuming this is non-zero. Because if it were zero, it would have order 1. So I'm assuming A is not in the kernel of phi. Assuming A is not an element of the kernel of phi. Claim is as a group element. Again, Z10 and Z20 are groups under addition, mod 10 and 20. They're also rings under multiplication, mod 10 and 20. So far, in this sentence, the author is emphasizing that the group structure, because we are talking about the group properties. From properties of group homomorphisms, ring homomorphisms are group homomorphisms. What properties? What do you think is special about these numbers, 10, 5, and 2? They all divide both 10 and 20, don't they? Yeah, there was a property back in the group homomorphism chapter. Looks like number 3 is the key one here. So we are talking about a group homomorphism back here. Again, ring homomorphisms are group homomorphisms. If the order of G is finite, then the order of the image, phi of G, divides the order of G itself, which has got to divide the order of capital G by Lagrange's theorem. And if the order of the domain is finite, as in our example it is, then moreover, you can also say not only does it divide the order of little g itself, which means it also divides the order of capital G, it also divides the order of the image of the entire domain, which is going to be a subgroup of G bar, and so we'll have to also divide the order of G bar. Lots to think about there. Yeah, these are finite groups. As groups, the order phi of A has to divide 10 and 20. Those are the possibilities if we're talking about it not being the zero element. Okay, next sentence is important as well. For any ring homomorphism from an arbitrary ring with unity to another ring S that happens to map phi of 1 to A, evidently 1 doesn't have to get mapped to 1. In fact, I mean, S doesn't even necessarily have to have a unity. Since 1 times 1 does equal 1 in R, this implies A times A equals A. Why? 1 times 1 equals 1 in R. We're just doing scratch work to try to understand this example here. We're assuming phi of 1 is A in S. They're saying it must be the case that A times A equals A in S. Use the fact that phi is operation preserving with respect to multiplication. In the previous sentence, we were only using group homomorphism properties. Here in the next sentence, we are talking about multiplication. We are thinking about the ring homomorphism properties, operation preserving with respect to multiplication as well as addition. Phi of 1 times 1, since phi is operation preserving with respect to multiplication, this must equal phi of 1 times phi of 1. But hey, this is A and this is A times A. So that's why A times A must equal A. In other words, A squared is A. A is an idempotent. Beautiful word. Idempotent. i.e., A is an idempotent in the codomain S. Okay, you had a homework problem. I just graded it last night. It'll go in your POs here today. Proving that in an integral domain, the only idempotents are 0 and 1. So if S is an integral domain, the only possibilities for A are 0 and 1. And if A were 0, phi would be the trivial mapping everything to 0, it turns out. And if A is 1, that seems like maybe everything would get mapped to itself. If, well, at least if the domain and codomain were the same rings, at least. They're not here, but there are rings that are not integral domains. In particular, both Z10 and Z20 are not integral domains. Right? 10 and 20 are not prime. Z10 and Z20 have 0 divisors. And they also might have idempotents that are not 0 or 1. Let's see. Yeah, A must be an idempotent in S. Now we consider cases. What if the order of A is 10 or 5 or 2? If the order of A is 10, then A must be 2, 6, 14, or 18. Why? Okay, well, the A is an element of Z20. We're thinking about homomorphisms from Z10 to Z20. If the order of A is 10, that means, well, one element that has an order of 10 is 2, right? 2, when you add it to itself a certain number of times, doesn't get you back to 0 until you've added it to itself with 10 terms. 2 plus 2 plus 2, etc., giving you 20, but then mod 20 is 0. Think about multiples of 2 where the coefficient is relatively prime to 10. 3, 7, 9. Yes, these other numbers, 6, 14, and 18, are going to all have order 10 under addition, group operation being addition. 6 is not going to get you back to 0 when you add it to itself until you've added to itself with 10 terms. 10 times 6 is 60, mod 20 is 0. Before that point, you're not, you add 6 to itself a certain number of times, you're not going to get 20, you're not going to get 40. You only first get up to a multiple of 20 when you've added to itself with 10 terms. Same with 14, same with 18. Yes, 2 times 1, 1, 3, 7, and 9 are relatively prime to 10. That's where those are coming from. Checking each case to see if they're idempotent Oh, none of these four possibilities pan out. None of those are idempotents, 2, 6, 14, or 18. So what does that mean? It means the order of A can't equal 10. We've ruled that out. It could be the case that phi of 1 gets mapped to 10 under a group homomorphism. That's possible. But since the image of 1 has to be an idempotent as a ring homomorphism, 10 is not possible as an order of A for a ring homomorphism here. How about if the order of A is 5? Well, 4 has order 5 in Z20. So do 8, 12, and 16. Of these, you can check only 16 is idempotent. You have to check these things. I'll just mentally check this. 4 squared, 16. Mod 20 is not 4. 8 squared, 64. Mod 20 is 4, not 8. 12 squared is 144. Mod 20 is 4, not 12. 16 squared is 256. Mod 20 is 16. Of these possibilities, only 16 is an idempotent. So that is one possibility for what 1 gets mapped to. Is it a guaranteed ring homomorphism? I'll wait a little bit here. If the order of A is 2, there's only one element of order 2 as a group element. It's 10, but 10 is not an idempotent. 10 squared is 100, mod 20 is 0. So the only possible ring homomorphism from Z10 to Z20 is this formula. And where does that formula come from? It's based on the fact that we're assuming 1 gets mapped to 16. If 1 gets mapped to 16, then an arbitrary element X in Z10, since X is 1 plus itself with X terms, X is in Z10. And since phi is a group homomorphism, I can write this as phi of 1 plus itself with X terms as well. Well, that's 16 added to itself with X terms, which is the same as 16 times X, 16X. I mean, yes, in the end, you have to also mod by 20. That's the only possibility for a non-trivial ring homomorphism from Z10 to Z20. Just one possibility. Group homomorphisms, there are more. Ring homomorphisms is just one possibility. That this is well defined and preserves both operations follows directly from the definitions. It is in properties of modular arithmetic, you might say. Phi of X plus Y is 16 times X plus Y. And yes, in modular arithmetic, you can distribute the 16 through here. Yes, and you're still modding by 20 at the end. But that is something you can do with modular arithmetic. It's properties from chapter 0. It's a little trickier verifying this operation preserving with respect to multiplication. The question is, does this equal 16x times 16y? Oh, yes, it does, because 16 is idempotent. That's why. Put a question mark there. This works because 16 squared equals 16 mod 20. The rest of the example thinks about homomorphisms, ring homomorphisms, the other way from Z20 to Z10. But the argument is similar. Phi of 1 is A, where A is some idempotent in Z10 by the same argument. Checking for idempotents in Z10. There are only 2 of them, 5 and 6. 5 squared is 25, mod 10 is 5. 6 squared is 36, mod 10 is 6. And or 5 as order 2 is a group element of Z10, 6 as order 5. And both 2 and 10 are divisors of 20. I think that the author meant to say 2 and 5. Yeah, the author meant to say both 2 and 5 because those are the orders there. These images are candidates for phi of 1, and indeed, both of those are ring homomorphisms. So again, there's the only non-trivial ring homomorphism from Z10 to Z20. These are the only non-trivial homomorphisms, ring homomorphisms back the other way from Z20 to Z10. I'm not doing this example for no reason. I have once in a while put these kinds of, maybe not every exam 3, but I sometimes put problems like this on exam 3. Not that you know, maybe with some guidance, maybe for simpler examples. Not that you'd have to write everything the author does, but you should know that with ring homomorphisms, if phi of 1 equals A, then A must be an idempotent. A squared must equal A, and that helps you rule down the possibilities for A. But once you know what 1 gets mapped to, like in this example, 1 getting mapped to 16, you do effectively know the formula for phi, 16x in this case. Question?
For those mappings, is there like a chance that there's any more than one?
I mean, yes, you wouldn't know if 16 is the only idempotent other than 0 and 1 without checking. I mean, it's possible there could be others. You have to check. I don't know of any quick and easy way to check besides just trying them all. Okay, but it is worth remembering. Once again, if phi is a ring homomorphism and phi of 1 equals A, then A must be idempotent in the codomain. Could be 0, could be 1, could be some other idempotent.